project and construction of Launch Pad 39A and 39B at Kennedy Space Center have been started in 60s. Both complexes have designed to handle launches for the Saturn V rocket, the largest and most powerful rocket then designed, which will propel Apollo spacecraft to the Moon. Propellants for the Saturn V's second and third stages were 1.25 million liters of liquid hydrogen and 1.74 million liters of liquid oxygen. Prior to being loaded into the launch vehicle, they were stored in spherical containers with a capacity of 3.31 million liters of liquid hydrogen and 3.22 million liters of liquid oxygen. They were located about 1,500 feet from the pad, and the main difference between them was the type of insulation used. Both employ expanded perlite powder insulation to help reduce environmental heat leak. However, the liquid hydrogen vessel is vacuum jacketed, while the liquid oxygen sphere is only double-walled and purged with gaseous nitrogen to prevent moisture ingress. These storage tanks served the same purpose during the 30-year Space Shuttle Program. The technology for those spherical cryogenic containers was developed during the early part of World War II with stainless steel materials and processes used in the 50s. They were vacuum jacketed with 3-foot thick perlite insulation that was the state of art in '65. Without insulation, the liquid would boil away very quickly. With the very best insulation system in the world, the liquid still boils away, just at a slower rate. In any case, for traditional cryogenic liquid storage, the tank can either be freely vented to the atmosphere to maintain the desired pressure for long duration storage, or the vent can be closed and the tank allowed to pressurize. The main problem during Apollo and Space Shuttle era was the important boil-off of cryogenic liquid with big limitation on operations. Over the duration of the Space Shuttle Program, NASA lost approximately 50% of hydrogen purchased due to continuous heat leak into the ground and flight vessel, boil-off during transport, liquid bleed and vent losses. Since production of liquid hydrogen is an energy-intensive process, these losses represented a large and unrecoverable cost on the order of several $1 million per year. This cost forced NASA to invest in the next generation cryogenic storage systems with the development of the Ground Operation Unit for liquid hydrogen at Kennedy Space Center. After years of utilization and looking into the necessities related to the new space launch system, these limitations are no more acceptable and the new design has to substitute the old one. Moreover, the space launch system requires a larger tank with 4.73 million liters of liquid hydrogen, becoming the world's largest cryogenic hydrogen tank. The new tanks will include two innovative technologies. The first one is the glass bubbles thermal insulation system. Research and development of gas bubble fill material for cryogenic tank insulation system began in the early 70s. In the recent years, a study has been made with 50,000 gallons liquid hydrogen tank where perlite powder has been removed and 3M K1 glass bubbles were installed. All the tests showed that the gas bubbles don't break and they are not difficult to manage. Moreover, glass bubbles are far less sensitive to vacuum level degradation compared to perlite powder. Glass bubbles insulation is going to replace the old perlite powder, giving a 46% of reduction on liquid hydrogen losses to boil-off. The second new technology utilized is the integrated refrigeration and storage system. This technology provides direct removal of heat energy via an internal tank heat exchanger together with an external cryogenic refrigeration system. Integrated refrigeration can be used for increased safety during loading activities, eliminate boil-off, liquefy gaseous hydrogen directly inside the tank, and increase hydrogen density with the subcooling. A NASA ground test facility has been used to evaluate this technology using a 33,000 gallon storage tank with integral heat exchanger connected to a 900 watt cryorefrigerator unit. It has demonstrated long duration of the liquid, zero boil-off and densification. With the electrical refrigerator unit, a spending of 14 cents for electricity can save $1 of liquid hydrogen. The internal refrigerator is based on a reverse Brayton cycle and provides helium refrigerant to the cryogenic vessel's internal heat exchanger, made by a manifold for helium delivery and return, plus smaller coils for internal distribution. Helium is sent to the heat exchanger and returned to the refrigerator always in the gaseous state, having a vaporization temperature lower than liquid hydrogen. After considering numerous options, a Linde cryogenic model LR1620 machine was chosen with an RSX helium compressor. To supplement the base cooling capacity, the option for liquid nitrogen pre-cooling was chosen for this unit, which required additional hardware but boosted the refrigeration performance by roughly a factor of 2. Both technologies are very important considering that the SLS system will require 730,000 gallons of liquid hydrogen and liquid oxygen to fuel the 4 cold stage and single upper stage engines. Now, a larger and more efficient tank will allow NASA to attempt SLS launches on 3 consecutive days. In the past, NASA had to stand down after 2 attempts, so additional hydrogen could be newly loaded into the storage tank. If you found this video to be helpful, don't forget to leave a thumbs up and then make sure you subscribe to our channel, so every time we publish a new video you can get notified. In the comment below, let us know your feedback on this video and if there are any other interesting matter you would like to discuss.